So yes, hi, I am Nathaniel Frissell, W2NAF, and I'm going to talk about I'm measuring the ionosphere with amateur radio. And I am a professor at the University of Scranton, but I got into all of this because of amateur radio. So as Russ probably knows, I first learned about ham radio through scouting. There was a cold, wet jamboree on the air back when I was in seventh or eighth grade, and I was at Camp Glen Gray in New Jersey, and it was just so wet and miserable that weekend. But the one thing that was really neat is there was one cabin out there in the middle of the woods, and there was a ham N2BSA. He had a station set up temporarily for the weekend with a little dipole, and I walked into that cabin and it changed my life because I heard the static coming out of that radio. I heard him talking to faraway places, and that's really what led me to eventually pursue a career in ionospheric physics and science. And it was because of that, and because of later experiences working with radio and scouting at Forestburg Scout Reservation. So this is one of the early stations I had at my house growing up. This is actually probably the second station I had in my bedroom, but this one was a little bit more developed. And I think it's neat because I've done a number of published papers now that use amateur radio data. And so I'm probably one of the very few people that you will ever meet that actually has a photograph of their bedroom in their PhD thesis. So this is actually in my PhD thesis. So I've been very fortunate. I've gotten to go on a number of very interesting quasi-D expeditions through my scientific career. And one of them was down to Antarctica. And so I got to go down to McMurdo Station, and which is of course down here. And this is the outside of their station, and they have that set up over there. And I was able to operate it. And I wanted to, we talk about how space weather can affect ham radio. And I think this is a really good case. Just listen to this. So the side tone you heard was me transmitting from McMurdo Station, but then the reception that you heard, that CW was coming in from, far away place, and you could hear these wild pitch changes, and those are all Doppler shifts caused by space weather activity. Probably there was auroral activity going on at that time, and that would cause the propagation path lengths to vary, to either get longer and then you get negative Doppler shifts, or shorter and then you get positive Doppler shifts. So this is a really great example of how one-way space weather can affect amateur radio. Yes, Scott, you have a question?
Yeah, actually, so it almost sounded to me like you were tuning. I mean, it was that drastic.
Yeah, it was.
Because I've worked a lot of HF, I've worked a lot of stuff over the pole. And you'll hear, I've heard lots of warble, but I've never actually heard pitch changes. That's pretty amazing.
Yeah. So one of the things, there's ionospheric variability all over the place, and we're going to see a lot of examples of that, especially in North America, where we are later in the presentation. But really, in the polar regions or in this auroral zone, all of the aurora is occurring because you're getting these charged particles precipitating from space along magnetic field lines into this region of the Earth. And when those charged particles hit the upper atmosphere, they ionize it, and then that actually creates additional ionization in the ionosphere. And so in this region in particular, you get very drastic swings in electron density and ion density. And that's what will cause these very dramatic Doppler shift changes. I'll play it one more time because I think this is a really great audio clip. Start it from the beginning. Yeah, isn't that crazy? So when I was in graduate school, I came across a number of projects, and I came up with this idea to start. I was like, we should start an organization that connects the amateur radio community to the professional space science research community, because I was a amateur radio operator, from high school all on up, and I really enjoyed the hobby. And when I got to graduate school, I was working with these things called super darn radars, which are high frequency radars used to study the ionosphere. And I thought it was kind of crazy that it didn't seem like the uh, people who are running the super darn radars in that science community, it didn't seem like they were really talking with the amateur radio community too much, and vice versa, even though there was so much in common. So that's where Hampside came from. And so this is a collective that allows university researchers to collaborate with amateur radio community in scientific investigations. And so we want to advance scientific research and understanding through amateur radio. We want to encourage the development of new technologies to support this research. We want to provide an educational opportunity for the community and the general public. So if we're going to have a science group, we should have some science goals that we're after. And broadly, we're interested in any scientific question of interest to the amateur radio community or to the field of space physics. So it's a fairly broad mandate. So some examples include solar flare impacts on the ionosphere, geomagnetic and ionospheric storms, traveling ionospheric disturbances, short time scale, small spatial scale ionospheric variability, and communications with a lower atmosphere. So those are all things we're interested in. Now, a little review. Since all of you, or almost all of you, are HF operators, you're probably familiar with this, but I know some people may not be, or it's good to go over some of the details again. So how do we communicate around the world? Well, one of the things we need an ionosphere. So the ionosphere is a layer of charged particles that ranges in the atmosphere from about 80 kilometers up to really about 600 kilometers above the Earth's surface. The ionosphere is created primarily by solar ultraviolet and extreme ultraviolet energy hitting the upper atmosphere and causing ionization of the neutral particles. So you'll get electrons knocked off of atoms and molecules, and then you'll get free floating electrons and free floating positive ions, and that's what creates the ionosphere. Now, we have different layers of the ionosphere. So during the day, this is typically broken up into the D, the E, the F1, and the F2 layer, and you can see what altitudes they are normally at there. And then at night, when the sun goes away, you get a lot of what we call recombination, and the electrons find the positive ions and they turn into neutrals again. And so then they leave the ionosphere. And so at night, you get less structure. You have just the F region and some of the E region. And this, of course, is an oversimplified picture, but it gives you a good illustration of the basic idea behind it. Now, we can actually predict where radio waves will go by using a technique called ray tracing, numerical ray tracing. And so you can look up these things called the Appleton-Hartree equations, and they will tell you if you have a particular electron density gradient, and if an electron density, and if you are operating at a particular frequency, you can calculate how much that radio wave will be bent by the ionosphere. So there's a program called FARLAP, which you can download for free from the Australian Department of Defense, that will let you do numerical ray tracing through a numerical model ionosphere. So in this particular case, we are modeling a 14 megahertz signal leaving from a station in Florida, which is over here, and it's being received by a station in Wisconsin, which would be somewhere out here. Let's see if I go earlier in the movie, there it is. That's where the station in Wisconsin is. When the computer predicts that there will be a path between the two, you see a red line. When the computer says the rays don't reach there, the red line will disappear. if you go too high an angle, your rays can escape out into space. And so that minimum angle there, or the maximum angle you can use before you escape out to space, that's known as the critical angle. So this one's actually a movie. This is during the a simulation during the eclipse on August 21st, 2017. There was a total solar eclipse that went across the United States, which many of you may have seen or participated in. And so when you have no eclipse, you have pretty much a standard daytime ionosphere. And when the eclipse comes on, the shadow of the moon comes over, you'll see the ionospheric densities decrease and the signals will escape into space. The band will shut down. So here's an example. Play that through. I really like watching these ray trace movies. I think they're really fun. They help to illustrate what's going on. You can see things jump. It was first refracting there. It's off of the E layer right now, but then at one point it actually jumped to F layer. Of course, this is still as good of a model as this is. It's still a very idealized cartoon. You know, the electron densities are very smooth here in real life. There can be irregularities. There can be all sorts of variability. This is a two-dimensional ionosphere. In real life, you can have things that go to the sides as well. So you need to do three-dimensional modeling. But still, it's a good way of kind of getting in your head what might be happening. This movie was showing you an example of what happens if you leave the frequency constant, but you vary the background electron density. Clearly, when you have less background electron density, there's less refraction, less bending. When you have more background electron density, you have more refraction and more bending. Any questions?
I have a question.
Yeah.
So I never usually think about E-skip on the 20 meter band.
Mm-hmm.
How heavy is, I mean, that's not going to be the dominant mode of propagation on 20 meters typically, right? I mean, it can happen, I guess.
Oh yeah, it can happen quite a bit. In fact, when I did the solar eclipse QSO party, the data we collected actually, I think, suggested that most of the 20 meters was in the E region.
Really? Okay.
Yeah.
Because you never usually think of the E region as being good for much of anything except for, you know, sporadic E and really sporadic E. So
yeah, and even more clearly, I'm not sure if I have it in this presentation, but my friend and collaborator Steve Serwin, WA5FRF, he routinely takes Doppler measurements in Texas on 5 and I think he usually does 5 megahertz WWV. And we have very strong evidence that for long periods of time, he's seeing, especially during the day, he sees E region refraction instead of F region. We've got very, very good evidence of that. So yeah, so E region can be very important. Here's another example. Now in this particular ray trace, we're holding the background electron density as constant, but we're changing the frequency. So here you have 15 megahertz up here. Here you have 10 megahertz down there. And what you're seeing is that as you go higher in frequency, you see less refraction. So on 15 megahertz, to go 1,500 kilometers in ground range, it only takes 1 hop. On 10 megahertz, it actually takes 2 hops. So what's neat is we can look at what amateur radio operators are actually doing and where their signals are going. And we can, you know, study space weather that way. And all of this is made possible thanks to primarily these 3 websites and /networks. So all of you are probably familiar with these. Again, we have the Reverse Beacon Network, which is a network of automated Morse code CW skimmers. So if you go on the air right now, you go on CW CQ, 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 DE, and then your call sign a few times, it should automatically pop up on this list and you'll see what stations are actually hearing it, what automated stations. And I have a skimmer here at my house in Pennsylvania. So if you did that right now, you might be able to see if if my skimmer can pick you up. So they record all of that data, who is transmitting, what station heard them, what frequency, what time, and the signal to noise ratio, which hasn't been super useful for us, but they record all of that, they archive it and make that data available. WhisperNet, similarly, you can go on their website, you can download all of your data of their digital weak signal propagation reporter network data. And PSK reporter, this PSK reporter is taking in all of the FT8 observations, and they're archiving that as well. So these are very rich sources of observations, and their data now goes back to 2008, a whole solar cycle. So I have some plots where I've plotted all of this for an entire solar cycle. It's really neat, the patterns you can see. But if we want to start off with something simple, one of the easiest things to see in these data sets are solar flare impacts. And so solar flares are, of course, interesting to amateur radio operators because they will create a sudden ionization of the D region ionosphere. Now, the D region, you'll sometimes hear people call it the darn D region, because it ends up not helping propagation, at least at HF, but instead absorbs it. And that's because in the D region ionosphere, you have a very high density of both electron density but also very high neutral density, neutral particles. And you're actually very likely to have an electron collide with a neutral before it's able to re-radiate your signal. So that creates something called collisional damping. So here's a case where I took both the PSK reporter, I think I took WhisperNet, yes, and RBN, and I plotted in a map for a 15-minute period on September 6th, 2017, in a 15-minute period before a major solar flare. And you can see here that there are 12,824 paths plotted on this figure, and they are all color-coded by frequency. The orange is 7 megahertz and the green is 14 megahertz. And then there was an X-class solar flare, and then this is a 15-minute period after. And there's a dramatic drop off in the number of communications. So here there were 12,000 paths. Now we went down to 2,200 paths. So you can see an 82% drop in the observed propagation paths over those two consecutive 15-minute periods. The place that's hardest hit, of course, is Europe, because that is the place that was right in the middle of the day, local noon, when the solar flare hit. I found another really nice way to plot it is in a time series. So this, what I'm showing here first is the measurement from the NOAA GOES satellites that were showing the X-ray irradiance. And so here's where you can see, using two different GOES satellites here, GOES 13 and 15. So here you can see one X-class flare, and there you can see another X-class flare at these two different times. And then this is the RBN and WhisperNet data from Europe only. Over here is the time series of that data. So this is showing you the distance between transmitter and receiver for the communications distance. This is time. So you have 12 hours of time along this axis here. And you can see that in 7 megahertz, communications are going strong, and then boom, you have your first flare hit. It takes, maybe 30 minutes to an hour to recover. And then boom, you have another flare. And then it takes this is an even bigger flare. It takes an hour to 2 hours to get recovery. This white dashed line here, this is the solar zenith angle. So you can see when this is highest on the plot, that's when you have local noon. Questions on that?
Can I ask a question?
Yeah, please do.
Okay, so you said it's actually a solar flare, and since it's X-ray, this is basically coming in at the speed of light. This is not a particle storm, right?
That's correct.
So that's about 8 minutes after the actual flare, and we don't know about it because we can't get the information faster than the speed of light anyway.
That's absolutely correct.
So I have actually been on the air when one happened, and that's what it sounds like. Basically, it sounds like somebody threw a light switch and turned off the. It makes you think, oh, my antenna fell down.
Yeah, they're like, they're
So
not talking anymore.
yeah, so but it actually is a D-layer enhancement, and so that's basically viewing electrons as the carrier and re-radiator as opposed to the wave model, I guess.
Right, yeah.
Okay.
And then those electrons would collide with the neutral particle and they would get damped before they could re-radiate the energy.
And is that the same basic method that the D region damps signals during the day?
Yes.
Okay.
Mhm.
Because people, I mean, I teach technician license classes, and people will say, well, why does the D region damp?
Yeah.
What's the mechanism? So there you go. Thank you.
Collisional damping.
Thank you.
So I wrote a paper about this, which is down here, and I did not come up with the D region collisional damping mechanism. Other people did. But if you go look at this paper, all of the references are in there. So you can actually go find, it actually links back to the original references that work that out. This is the United States over here. And so this is for the same time period. But here you can see the United States was at night for here. And then here's dawn coming up, and noon is somewhere around here. So the United States is primarily shielded from most of these solar flares. So it's 7 megahertz at night. The electron density is weaker or lower. And so you actually get longer refraction on 7 megahertz. So 7 megahertz goes long at night. And then here you can see you really don't see this first X-class flare at all. And then here you just barely see it here in the dawn transition. You do get it knocked out a little bit, but it's not nearly as affected as Europe. But you also do see here the transition as hams, or not just as hams, the transition as the propagation goes from longer distances to shorter distances during the day. So what else? So I thought solar flares are pretty straightforward to see, but I wondered what else can we see in the RBN, WhisperNet, and PSK reporter observations? And what I really wanted to see were these things called traveling ionospheric disturbances. So I studied medium scale traveling ionospheric disturbances when I was in graduate school using super darn radar. And I was like, I bet I can see traveling ionospheric disturbances in the ham radio data as well. And so that's what we're going to look at now. So what traveling ionospheric disturbance is, it's a wave in the ionospheric electron density. And it's often associated with neutral atmospheric gravity waves. And this is something, medium scale ones, they can cause QSB or fading on the HF bands with periodicities of say 15 minutes to a few hours. Large medium scales begin more around 15 minutes to an hour. Large scale ones will be, a few hours long. And so this is a model. I took the International Reference Ionosphere, or IRI, which is an ionospheric model, and then I just perturbed it with a sinusoidal propagating wave on top of it. And so this is a 250 kilometer altitude cut, and you can see these waves propagating down from the northern region down towards the equator. And this has wave parameters that are very typical of what you would see of a medium scale traveling ionospheric disturbance. This is the outline of a super darn radar in Kansas. I believe it's operating on 14 megahertz in this model. And if you look along this path here, you get this profile. And what you can see is that as these waves come through, they'll actually cause the rays to bunch together or focus together. So you get this focusing and this defocusing effect. So you can imagine that if you're a radio receiver sitting right here, whenever the waves are focused together, you're going to get a strong signal. And whenever they're defocused, you'll get a weak signal. You can also imagine this means that it changes how far you can communicate. So you're seeing an oscillation in communications distance between, say, like 600 kilometers and 1,000 kilometers. Questions there?
Yeah, give me a hint on what a neutral atmospheric gravity wave
Yeah,
would look
I was
like
going to
and
ask the
what's
same
its
thing.
periodicity.
Well, and you
Right.
say when a gravity wave. Is that what
Right.
we think of with a gravity wave?
Probably not. So
Okay.
here the gravity wave means here neutral atmospheric gravity wave says, imagine you have a parcel of air in the atmosphere and you were to perturb it, say push it up, or buoyancy might push up, or for some reason it gets pushed up, gravity is going to pull it back down. So gravity is the restoring force, and then buoyancy pushes it back up and it oscillates because of that gravity and buoyancy. So it's just a wave in the atmosphere due to gravity, and they're very, very, very common.
Due
Let's
to
see.
gravity or due to changes in pressure of the upper atmosphere winds?
Well, the wave itself, so maybe the winds might perturb it and launch the wave, but then once the wave gets going, gravity is the restoring force. That's why they're called gravity waves. But some of the things that can cause gravity waves, you can have, you could have, say, tornadoes or earthquakes. Those can cause gravity waves. In my dissertation, I found that the polar vortex was when you had more polar vortex, we saw more of these traveling atmospheric disturbances. So there's an association of those with gravity waves. That's actually causing it. That's another question, but that certainly let us see these things. You can have auroral activity can cause gravity waves. There's a lot of different things that can cause them. And those gravity waves in the neutral atmosphere will then couple with the ionosphere, and that's what lets you see these sorts of structures move through. So there's a lot of super darn papers, and I did my whole super darn dissertation looking at these sorts of traveling atmospheric disturbances in the super darn data. But then I said, well, can we see it in the ham radio data too? And the answer is yes. So this is the same sort of plot you saw before, but now I have a smaller bin size here. So I guess I don't have it written here. I think it's like 2 minutes by 25 kilometers or something like that. But you're seeing now we're throwing RBN, WhisperNet, and PSK reporter all together in one bucket here. And we have distance along the y-axis again, and then time along the x-axis. We're looking at 12 hours here. And look at the bottom edge skip distance here. So you can see that the distances the stations are communicating over the United States, it's oscillating. Do you see that?
And that's the minimum distance, right?
Right, that's the minimum skip distance.
Right, and the maximum distance looks like it is maybe varying a little bit too. I mean, it's kind of a little harder to tell, I guess.
It's definitely harder to tell. It's definitely fuzzier. You can see it looks like there might be a second hop here where you also see an oscillation as well. Here's another plot of it. Here's a movie. So what we're showing here is we're showing the ham radio data up here again, and then we're showing total electron content measured by GPS receivers down below. And remember I said that when you have more electron density, you generally get more refraction. That would lead to shorter distances. When you have less electron density, you have less refraction. That would lead to farther communication distances. So what you can see in general is that when the map down here is more red, this skip distance comes in closer because the electron density is higher. And when the map down here is more blue, the skip distance goes out. The GPS TEC data is really, again, really fun to look at. You see all sorts of interesting features. There's the day-night terminator. You can see additional wave structures in here. Here it's turning red again. The communications distance is coming in. And then as we come up here, there's very red. As we leave that and we go out here, it's going to turn blue again. So really this wave is a very large scale wave. It's causing the electron density over the entire United States to go up and down. With a periodicity of about 2 hours, 2.5 hours. So what caused this? So this was likely generated by an auroral disturbance that happened just a few hours before. And so we were able to measure auroral disturbances using ground magnetometers up in the auroral zone, because the aurora carries, when the aurora happens, you get a current surge. And so that surge in current will actually cause a magnetic deflection down on the ground. And if you look at all the magnetometers in the auroral zone, you can create something called the auroral electrojet index, or here it's the supermag electrojet index, showing you when the current enhancements are occurring. So there was one between, let's say, like 10 and 11 UT, and another one between 12 and 13 UT. And then we were also able to use, this is also magnetometer data here. And then down here, we were able to use the poker flat incoherent scatter radar. We were able to measure electron density enhancements at that time and Joule heating in the ionosphere. Yeah, Dean, you have a question?
Yeah, so I'm expecting that most of the auroral activity is also due to solar flares too, right? Or is it also coming from other sources, deeper cosmic things or something?
So auroral, solar flares really are not going to cause aurora. You're going to have anything that would have charged particles in them that would more likely cause aurora. Aurora can be a little more complicated. I'm gonna bring up another. Let me bring up another video really quickly here. So if you were to go to YouTube, and if you were to look up something called a substorm, there's a really nice NASA animation that comes up. So you have the sun, and then you'll typically have some sort of a coronal mass ejection or something like that. Okay, so right here you have the solar wind. So this is not a solar flare or electromagnetic energy. This is actually charged particles, protons, electrons, things like that. It's a plasma, and it's carrying with it an embedded magnetic field. That embedded magnetic field, in order for it to, so you have one solar wind plasma over here, and then you have the Earth, and you have its magnetosphere over here. And that magnetosphere has its own separate plasma population in it with its own embedded magnetic field. So these magnetic fields will normally not mix unless they're pointed in opposite directions. So the Earth's magnetic field comes out of the South Pole and goes into the North Pole. And so it's pointing upwards like that. And then the solar wind magnetic field, if it's pointed southward, you'll get what's called reconnection. So there reconnection happened, and you can see the solar wind field line connected with the Earth's field line, and that's now going to get stretched over to the night side of the Earth. And that's going to keep happening over and over again. So it's peeling away. And as that magnetic flux piles up on the night side of the Earth, you're going to see that the tail gets stretched and pushed together. It's getting pushed together. And then right there, remember that out here, the lines are going out of the south into the north. That means right here at this point, they'll be pointing in opposite directions. So you'll get another reconnection point over here. At that point, the field lines, they'll snap like a rubber band, head back to Earth. And the charged particles, they like to flow along magnetic field lines like wires. So all the charged particles that are stuck on this field line are now going to go speeding down to Earth and cause the aurora. Right there. And when that and that's why you get more auroral brightenings on the night side than on the day side, because this process happens primarily on the night side. And this also is where you get all these charged particles, they dump into the upper atmosphere. They need to go somewhere. So it's like an electric current. It is an electric current. It's not like an electric current. It is an electric current, and it creates a circuit. And so that circuit has to go places. And so there are different current systems that connect space to Earth and vice versa. And so you'll see these current surges within the ionosphere, and that's what the magnetometers on the ground are picking up.
All right, cool. That's there's a lot more for me to learn there. Very cool.
Thanks. So at the same time, you also can have radar systems that are able to measure how many electrons are in right above the radar, and how much heating is going on there due to the aurora. And that is that's what's being measured here. Here's electron density measured by the radar. Here's the Joule heating. And so all of this stuff happened just a few hours before we started seeing these oscillations in the ham radio contact data. And if you were to look at the direction of travel of the wave that's going over the United States, and if you were to estimate its phase velocity, you could actually draw a line that would point back to approximately where the auroral source is occurring. And so this is likely the source. And that's also pretty well known. There's a lot of literature out there that supports this particular mechanism. So let's see. I think I'll wrap things up fairly quickly here, and then we can just answer lots of questions. So I've got a couple of research grants to help support this TID type of observations and work. I have a NASA grant and I have a career grant, and some of them are working more on doing empirical modeling. And my colleague, Bill Engelke at AB4EJ at the University of Alabama, he's actually just developed a machine learning program that using TensorFlow that will look at all of these sorts of plots and automatically tell you where the TIDs are occurring, and he can then create a climatology out of that. And we're using that to do some science now, and we have to use that to create a model. And then I have another grant where we're going to be doing more physics-based modeling and trying to compare that to the amateur radio data as well. All of this is great. I absolutely love working with the PSK and reporter data and WhisperNet data and RBN data, but it's not really, it never really was designed for science. Maybe WhisperNet kind of was, but the others certainly weren't. And so we said, well, those data sets are really noisy. Can we create a system that hams and other citizen scientists can use that would make more precision measurements of space weather activities? And so that's where we came up with a Hampside personal space weather station. And what we're doing is we're creating a software defined radio that operates primarily in HF band, and you can take its raw IQ output and you can use it to derive all sorts of different interesting data products, including snapshots of the HF spectrum and Doppler shifts of things like WWV and WWVB and CHU. You can use it to monitor ionosons. You'd also be able to simultaneously use it to monitor the amateur radio data and to do HF band noise characterization. So we're actually designing a new software defined radio to do that. To make all this stuff work, you really want to have very stable precision oscillator. The standard oscillators that you get in your typical ham rigs, they're really not stable enough to make the Doppler shift measurements the way they need to be made. But if you use a GPS disciplined oscillator, you can do precision time stamping and get Doppler shift out of that. You can also use, if you have a dual frequency GPS or GNSS receiver, you can actually measure total electron content between your station on the ground and the GNSS satellite in the sky. We'll have a single board computer like a Raspberry Pi to do local user data reduction. We have a ground magnetometer to sense changes in the Earth's magnetic field for reasons like I just explained with the aurora. We now have a VLF receiver, very low frequency receiver that can receive natural radio. And all of this will get connected to the internet and go to a public database. And this is a highly collaborative project. So we have a lot of different universities and organizations working on this. So University of Scranton's the lead group trying to aggregate all of this together. University of Alabama is developing the software. Tapper and Zephyr Engineering, they're actually creating our new software-defined radio, which they call the Tangerine SDR. Case Western is developing a low-cost version of the system called the Grape, which just monitors Doppler shift. NJIT is working on the magnetometer. We've funding from NSF and ARDC, and MIT Haystack is a science collaborator. And so here's some examples of some of the data that we might collect with the system. So the Doppler idea, again, here's WWV in Colorado. Here's a receiver. They have at Case Western W8EDU. And the idea is that as the ionosphere moves up and down, or as anything that causes the path length to increase or decrease will cause a Doppler shift on the signal. So here's an example from the 2017 total solar eclipse. During dawn, as the ionosphere builds up and moves lower, you get positive Doppler shifts. At night, as the ionosphere moves up and the densities get less and the path lengths get longer, you get negative Doppler shifts. And then during the eclipse, you have the opposite happen. So that's one example. You could do this sort of measurement with the low cost personal space weather station. This measurement, we're actually creating oblique ionograms. You need to be able to make wideband measurements. And so when we get the Tangerine SDR up and running, it will be able to make measurements that are like this. This was actually done on an Edis N200, but hopefully we'll have actual tangerines soon. Here's an example of the ground magnetometer. So we have a number of prototypes of this running already. I have one sitting in my yard right out there. We talked about the Doppler shift measurements and the eclipses. This is example data from an actual grape prototype. And so here you can see these traveling atmospheric disturbances moving through here. And another thing that's neat is we're actually working with NIST, and they've actually put this specialized waveform on. They're broadcasting it. I think they're still broadcasting it today. I haven't listened in about a month, but at least a month ago they were still broadcasting it. This is a special waveform being transmitted on minute 8 from WWV and 48 from WWVH that we're trying to figure out other ways that we might be able to use the WWV signal to characterize the ionosphere. If you'd like to be involved in Hampside, you can go to our website, hampside.org, and click Join Hampside. Hampside now has actually over 550 members. This slide is about a month old, so we have more members now, but you can go join our group there. We have regular telecons, so you can find me every Monday night at 9 p.m. Eastern at the Tangerine SDR Telecon, Thursday mornings at 10 a.m. Eastern at the Grape Telecon, and every other Thursday afternoon at 3 p.m. at the General Hampside Telecon. And all of these links are available. If you click this blue button here, all the links to these telecons are available on that webpage. I can tell you I'm generally much more awake for the 10 a.m. and 3 p.m. telecons in a Hampshire the 9 p.m. ones. Sometimes I struggle staying up that late, but these I'm very energetic at. So, and then another great way to participate is we have the annual Hampside Workshop, and we held it this year at Huntsville, Alabama, March 18th through 19th. And you can see recordings of it at hampside.org/Hampside2022 and see the presentations. Next year, I really hope we're going to be able to have it in Scranton at the University of Scranton. We shall see how that works, but it'll be around the same time. We did it hybrid this year, so people could actually come in person, but you could also attend virtually. And I think we're going to continue that model in the future. This is my kind of last science slide. This is just thinking ahead to the future. We know that there are eclipses, an annular eclipse coming up October 14th, 2023 and April 8th, 2024. And we are, working on our plans for this. So I'm working on a grant proposal for what we're going to do with the grape personal space weather station for this right now. And then we'll be working on doing another solar eclipse QSO party as well. And hopefully we'll get something in for the VLF system also. So lots of acknowledgements and people to thank. So thank you. And any more questions?
Well, that was awesome. That was very, very cool. So thank you so much for, you're thanking us, but we got to thank you. So.
Yeah.
Thank you.
Let me understand the GPSs that you were talking about. They are just ground-based GPSs that are put down by someone, or are these just, how does that actually work?
I'm guessing you're probably asking about the GPSs that created this map, right?
Right. Yeah. What are those? What are at those dots?
Okay, so there are lots of GPS stations around the United States and around the world that are not there so much to find location. They're just permanently put in a spot to help understand how the Earth is moving or how the GPS network itself is working or not working. Because any problem in the ionosphere can cause an error in the GPS. So if you have a network of GPS stations that have been surveyed and you're like, I know this GPS is located at that point, that provides useful information for airplanes and surveyors and people studying continental drift and all sorts of things like that, geologists.
So how do you plug into this? Does it come back on the internet, or you just polled them, or?
Yeah, so there's a couple of groups. MIT Haystack is one of those groups. I think JPL is another group that will go and they will grab the data from all the different data providers. There's like one called CORES, the continually operating reference system. There are different networks of GPS receivers that will provide them the data, and they will take that data and then they will do this to it. The idea is you need a special GPS receiver that actually is transmitting on at least two frequencies. Traditionally this is L1 and L2. So L1 is 1575.42 megahertz and L2 is 1227.60 megahertz. And the ionosphere, depending on the number of electrons in the ionosphere that passes through, it will cause a delay of one signal versus the other. And by measuring the delay between the two signals, you can actually back out the total number of electrons between the receiver on the ground and the satellite in space.
Okay, I get that.
There's the actual, so your slant total electron content. There's the actual.
Just to mention, like in Lane County, the county surveyor operates a precision geodetic receiver at the courthouse, and there's online records that you can download if you're that surveyors use, for example, of the GPS records, and they tell you what the velocity of the courthouse is. It's a few millimeters a year.
Yeah, exactly. So there are stations, thousands of stations like that around the world, and groups like the MIT Haystack Observatory, they have worked it out that they are routinely aggregating all of that data and running these calculations. And then you can call up our friends you can call up Anthea Coster and be like, Anthea, could I please have this data? And she'll be like, here you go. Or you can also actually get it. There's something called the Madrigal website. Let's see, Cedar Madrigal. Madrigal database at Cedar. Now, if you're not a space scientist, you'd probably never think that the word Cedar and Madrigal together would mean that you would get this data, but there you go. And you can actually go through here. It's not the most straightforward way of getting it. You list experiments. You end up having to put your name in a couple of times. And then you have to pick like, let's see, it should be distributed ground-based satellite receivers. And then the worldwide GNSS receiver network, 1998 through 2022. And you hit list experiments. And then it will come up with a list of all the data. There you go. So you can pick a date. Oh, 2002 sounds like a good date. Click one of these, select file. So on the Madrigal system, they just give you this binned 1 degree by 1 degree by 5 minutes.
A lot of data.
Plot data. Yeah, but this actually isn't the finest resolution. Like this is all binned data. So if you want to be able to create the, let's see, click here for TEC maps animated GIF. So you will see like diurnal variations in these maps, and you will see the what do you call it? And you'll be able to see probably some effects of geomagnetic storms, but in the way this data has been processed, you'll never see the traveling ionospheric disturbances. So you'd probably have to contact Anthea Coster and MIT Haystack to try to get the data in a form that I showed you. But this is basically the first way of looking at it.
So Nathaniel.
Yeah.
Any more developments on the tangerine SDR?
Yes. So I didn't really go over why we don't have tangerines yet. The short story is the tangerine is heavily dependent on an Intel Max 10 FPGA chip. And there is a part shortage. We're having supply chain issues. So the good news is there are two parts of good news. So part number one of good news is we have been told that our order of Max 10 FPGAs will be delivered May 20th. So we actually have a ship date for them. So we'll be at Hamvention when that's happening. So I'm hoping that Scotty is going to give a talk at the Hampside forum. And what I want his entire talk to be is just a live webcam stream of the front door of his house in Arizona. And then during his talk, we're going to see the FedEx delivery man bring the box of Intel Max 10 FPGAs to his front door. So that's what I want. Hopefully that will actually happen. But yeah, May 10th or May 20th, we're supposed to get those chips. Once we get those chips, we'll actually be able to make hardware and make progress. The other bit of good news is even if we don't have those chips, we have about 10 Max 10 FPGA development kits that have the chips already on them. And Scotty has designed an adapter board that will let us use those development boards, plug our RF modules and our clock modules onto the development board, and use that kind of as a stand-in Tangerine SDR. So it'll be very similar to the final model, but there will be a few differences. It'll only support like one RF module instead of two. and it won't have this exact same dimensions, or basically same dimensions or form factor as the final version, but it'll let us continue developing software, and those adapter boards are in production right now.
Because N5EG gave us a good presentation, and he said that was hanging everybody up. So that sounds like finally that's the 99-week lead time is sort of resolved.
Yes, at least
Yeah.
for the 25 chips that we ordered or whatever. So we'll be able to make our prototypes, which we're very grateful for. And then hopefully after we make our prototypes, hopefully we'll be able to get more when we need them.
Nathaniel, you sort of mentioned without background that I heard some sort of grape system, which appears to be something similar but different.
That's right. See, I'm not sure if I have the I have the backup slides for the group in here. What I can do. So we had one of our volunteer citizen scientists put together a poster presentation about his grape for the American Geophysical Union meeting. And if you click here, and right. So yeah, the idea is for the grape, you're just listening to WWV or CHU. Here's a map of where we have different grapes right now.
It should be pointed out that WWV and CHU are standard time and frequency stations, right? Incredibly precise transmitting frequencies.
Incredibly precise transmitting frequencies. So with your, if you were to just turn on your regular radio right now and you were to monitor the frequency and you were to look at very small frequency shifts, you could not be sure if that shift were being caused by changes in the ionosphere or variations in your radio's oscillator. But the WWV and CHU systems are tied into, I believe, atomic clock type of oscillators, and they have extremely stable oscillators. So such that if you had a receiver that was also extremely stable, you could be sure that the variations you're seeing were due to the ionosphere, not an instrumental effect. And so the reason that the grapes work is because of this little silver box right here, which is a GPS disciplined oscillator. And what that does is it listens to the GPS signal and it synchronizes its oscillator with that. And that also gives you atomic level precision. So the little purple board right here, that's the actual grape. And this is and then you have the GPS disciplined oscillator here. And the purple board, the grape, is basically just acting as a mixer. So you have a 9,999.9 megahertz signal coming out of the GPS DO, and that gets mixed with the 10 megahertz WWV signal, and it outputs a 1 kilohertz signal. And any deviations from 1 kilohertz is due to the and then that goes into a sound card that digitizes the Raspberry Pi, which records it.
So Nathaniel, you kind of broke up in that last comment. So can you try that again? Just the very last 30 seconds.
So the grape, this purple board, acts as a mixer. It's receiving the 10 megahertz signal from WWV on one port, and on another port, it's receiving a signal from the GPS disciplined oscillator that's 1 kilohertz below the 10 megahertz WWV carrier. and this mixes it and outputs it as an audio signal, a 1 kilohertz audio signal to this sound card. Then any deviation from 1 kilohertz would be attributed to the ionosphere. So GPS amplified antenna, Leo Bodner GPS disciplined oscillator. Here's the grape itself. So external antenna, there is a band pass filter here. You can choose between 2.5, 5, and 10 megahertz. You have the mixer. You have another audio band pass filter here, some gain, another band pass filter there, and then that goes out to a sound card. So it's very simple.
Thank you.
And all of the instructions for building this are available online. I should note this is the Grape version 1. We're actually working on a version 2 right now. The version 1 can listen to only one frequency at a time. The version 2 should be able to listen to 4 simultaneous frequencies. And again, I'm running one right here. So let's see if it's working. If I go to VNC, great, it's working. So yeah, these are the measurements. The black line here is the Doppler shift. The red line is the power, and here you can see this is nighttime. Here's the dawn transition, daytime. And they've got lots of measurements here. It's of course hard to make sense of any one particular day's worth of measurements from any one particular station. But I can in a second show you a plot that is very convincing.
With our motiony ionosphere.
Yeah. The way this is doing it, we just have a FL Digi. We have a special version of FL Digi, which is just set to track that one particular frequency. In the future versions of the Grape, we're actually going to move away from this technique because it turns out that tracking just one single frequency isn't sufficient. You really need to know a spectrum around it. We do actually have that implemented, but it needs a little more. It needs to be more widely distributed and better organized. But that's where we're going with that. Let me show you that plot that's very convincing. I got it in my text messages earlier this week. So one with so this is a plot Christina Collins KD8OXT made using data from John Gibbons' Grape. John Gibbons is N8OBJ. John is N8OBJ. He's the engineer over at Case Western. He's the one that actually designed this whole system. So this is really his handiwork in designing this system. And then Christina KD8OXT, she's a PhD candidate funded by this project. She made this plot. So they've done really great work. But here what you're seeing is essentially 24 hours of day on the y-axis, and you're seeing 2 years on the x-axis. And color here is Doppler shift. So red is positive Doppler shift and blue is negative Doppler shift. And right in the middle here, this is nighttime. And then on the edges, this is noon and that's noon. So you can imagine that they kind of wrap around together. And so you really see that as you hit the morning transition, the dawn transition here, you get these negative, wait, this is the dawn transition here. That's right. I keep forgetting the night's in the middle here. So as you get the dawn transition here, you get this very hard edge positive Doppler shifts. And then it goes on through the day. And then when you come to the to dusk, you get a more soft or diffuse transition in negative Doppler shifts as you go into night. And you can see that you see the seasonal effects here in this sinusoid right there, like that. And so you're getting oh, what do you call it? So you have more hours of daylight during the summer and more hours of night during the winter. And so this is what you get when you put 2 years of observations from one grape together.
Are there any other questions? Well, hearing a little bit of silence here, and given the hour that you have there on the East Coast, don't want to keep too much of your time, but this was very, very cool to see. And
Gives us a lot of homework to do. It's a very good presentation, Nathaniel.
Thank you, Russ. Thank you so much. It's so good to see you again, too.
Yeah, really.
I know.
so can we give Nathaniel a round of applause for his efforts here? Oops, I disappeared. Sorry.
Thank you so much. I'm so glad to see you have an active ham radio club over at the University of Oregon. And I hope to catch you on the air as we get our station up and running, as you get your station up and running, and hope we can all get really nice rooms and towers and all that stuff.